about semiconductor physics. More specifically, I'm going to be talking about the semiconductor bandgap, but this is kind of the thing that rules the entire process of semiconductivity, right? Or the entire property. So we're going to discuss that. Now, what we begin with is the fact that semiconductors are solid materials, right? They're solid matter. And as with all solid matter, we have the case that the atoms of the matter are quite closely packed in these nice lattice-like structures that are pretty much like perfectly symmetrical and beautiful. Now, every atom comes with nuclei and electrons, of course. I'm just going to circle these around. So these are the electrons orbiting the nuclei. We don't have to use the full quantum picture for this because it's just a visualization. No orbitals, no nothing. Just call them shells for this case. So these electrons orbit around these nuclei. Now, in every atom in the lattice, there's going to be a valency shell, right? The electrons that are the furthest away from this nucleus. And these valence electrons are going to be the ones that we're going to be focusing on in this video, because they govern this entire process. Now, these outermost electrons, as all electrons do, can correspond to specific states, right? That is what quantum mechanics tells us. It tells us that, hey, these things act as waves, and these waves have specific states. In atoms, if we just focus on one atom, these states are discrete, as in we have one energy, then we have the next energy, and between that, you are not allowed to go. You are not allowed to be in any of these energy states, only here or here. Now, in a full bulk scale material, like say silicon, which is one of the most important semiconductors, in full scale bulk material, the possible energy states of electrons are a bit more nuanced. And they're given by this thing called a band structure. This diagram has a k vector on this axis, and the k vector just refers to the directionality of the wave of the electron. It's just a property innate to an electron. And the energy, well, that's the energy of said electron. The valence band refers to the possible energy states of these electrons, these outermost valence electrons, right, that we just talked about. And each one can have a specific k vector and a specific energy. And it's drawn out as this sort of continuum of states here, where basically every point on this is a possible state that an electron can take up. Now, what we do notice is that in between these two bands, right? Bands are the parts of this diagram where electrons are able to take up states. Between them, there is this forbidden energy level, the band gap. Basically, what is meant by this is that, hey, we can have electrons have any of these states, the valence electrons of the silicon can have any of these states here, and they can also have any of these states here in the conduction band, but they cannot have any states here. And this just comes from calculating the wave functions through the lattice. And I'm not going to discuss it in this video. I'll probably do it in some other video. It's going to take a bit too much time. But what is important is that, hey, since these are all possible states for the valence electrons in our silicon lattice to be in, then we can promote them up to this conduction band if we just overcome the band gap, if we give them enough of an energy push. And what exactly do these states correspond to? Well, you can think of it like this, right? I've labeled these electrons 1, 2, 3, and 4 in this sort of 1D lattice, and these 5 and 6. Well, the lower energy states are going to correspond to the ones that are more tightly bound to the nuclei, right? So I've labeled this one 1, this one 2, this one 3, and this one 4. So this electron has this state, this electron has this state, this electron has this state, and so on. They correspond to one another. Now, if we give them enough energy, then what we notice is that electrons will move further away from the nucleus, right? Electron number 5 and electron number 6 are now above this band gap, and they're in this conduction band. And that corresponds to them having a higher energy and being further away from the nucleus. Now, that is good for us, because that means that, hey, if I now apply, say, a charge difference at both ends of my silicon structure, if I put a big negative charge here and a big positive charge here, then these outermost electrons will actually be able to move towards the charge, and therefore generate current, or generate an avenue for current to pass through, because these electrons correspond to states that are so tightly bound to the nuclei that you can't really get these to move anywhere. So they won't conduct for you, which is, therefore, a semiconducting material, right?